So in this video, we're going to talk about arc length function. And so let's draw a little picture here. So I've got a curve. All right, this curve is defined from A to B. So let's call this curve f of x. And so that would mean that this point right here, that point would be A comma f of A. All right, and then this point here would be B comma f of B there. Okay, now say we've got some arbitrary point on the curve, and this point here is just some random x in this interval between A and B. And so that would be x comma f of x for that point right there. Now, I'm going to let y equals f of x and s of x be the distance along the curve from the initial point P naught, which is going to be A comma f of A. That's my initial point right here. Okay. That's my P naught. Going to Q, which is x comma f of x here. Okay, so s of x, s, right, I'll use green, okay, for s. So this is that distance right there, all right? So s of x is the distance along the curve from some initial point to some q point. Okay, so that's my q point there. And this is my initial P naught point here. All right. Now, s of x is defined to be, okay, s of x is defined to be the integral from A to x, some arbitrary x, square root 1 plus the derivative evaluated at dummy variable t squared dt. Okay. Now, this x, depending on where this x falls, determines how far along the curve we are. Okay. So a bigger x would mean we were further along the curve and a longer value. So what we've done is we've created a function that gives the length of the curve from some starting point to any other point on the curve. So depending on where we're moving that curve, so depending on where we're moving that x value, it moves us along that curve there. Okay? All right, so let's work a problem and see if we can't come up with a function here. So I want to find the arc length function for the curve y equals ln of cosine x, taking 0, 0 as the starting point. Okay, so we have some starting point and then we just go out arbitrarily from there. So first thing I do is I notice that y is a function of x. So that means I need to find y prime. Well, the derivative of natural log of something is 1 over the something times the derivative of the something. So that's 1 over cosine x times the derivative of cosine, which is negative sine. And so what does this get me? This gets me negative sine x over cosine x, which is negative tangent x. Okay? So I'm going to take my integral, my arc length, s of x is equal to the integral from a to x of square root 1 plus the derivative squared. And so this is going to be the integral from, well, what is it? It's 0, 0. So the x value is 0 here. So from 0 to x, integral 1 plus negative tangent t squared dt. So this is the integral 0 to x square root 1 plus tan squared t dt. Now, what do I know about 1 plus tan squared? That's a Pythagorean identity. This is equal to the integral 0 to x square root secant t squared dt. The square root of the square, those cancel each other out, and I get the integral 0 to x of secant t dt. This just so happens to be one of those rules we're supposed to memorize. And so the integral of secant is ln absolute value secant t plus tangent t, evaluated from what? From 0 to x. So f of b minus f of a gets you ln absolute value secant x plus tangent x minus ln secant 0 plus tangent 0. And this ends up being 1, and that's 0. The natural log of 1 actually equals 0. So that all goes to 0 here. So this all goes away. And so what do I get? I get the natural log of secant x plus tangent x. So my arc length function here, s of x, is equal to the natural log of secant x plus tangent x. Pretty cool. So what does that even mean, right? You could be asking yourself, well, I don't even know what that means, Mr. Clark. Well, it's saying that if I start this curve, y equals ln cosine x. So let's see what that looks like in a graph. So ln of cosine x, enter. When I plot this, so starting at 0 here and going right, so if I go this way, all right, maybe let's try like, looks like we've got a vertical asymptote going on here, which would make sense. So maybe let's go to like pi over 4 or something, see what that does. Okay, so let's do like s of pi over 4 here. So what is that going to be? Well, that's the natural log of secant pi over 4 plus tangent pi over 4. So look, I'm doing extra here. This is the answer. That's the arc length function. I'm just showing you how to use this arc length function, what it actually means, right? So if I plug in pi over 4, this is going to get me, well, secant is 1 over cosine. Cosine of pi over 4 is 1 over the square root of 2. So this 1 over square root of 2 actually gets you square root of 2. And then the tangent of pi over 4 is 1. So let's see, ln square root of 2 plus 1. What does that equal to? Ln 1 plus square root 2. So that's 0.881. Okay, so what does that mean? So when I looked at that graph, it looked something like this, right? Okay, So, what did we say? It started at 0, 0, okay? And so this is a function that whenever I input an x value, so I input, so my s of x, this is my function here. Whenever I input pi over 4, it tells me the distance, this distance from 0, 0 to that distance, pi over 4, comma, ln cosine pi over 4, okay? So pretty cool how it's a function now that's measuring the distance instead of just giving us one value. It's kind of like, instead of, evaluating the definition of the derivative at a single point, we find the derivative and then we can plug in any point we want. Okay, so just to give you a little refresher on that, like if I had f of x equals x squared, right? It would be like, instead of finding, okay, f prime of 2 is equal to 4, it would be like saying, I want to find f prime of x, which is 2x, and now all I have to do is plug in 2, and I get 4, okay? So, maybe in some instances it's quicker to go this route, but in others where you need to know, maybe you need to study how the derivative changes, then you might want to get some function of the derivative, kind of like some function here of the arc length. All right, and so that's what's going on there. All right, so that wraps up arc length.